All right, so we're going over this waves review, so just try to keep up. If you have any questions, make sure you ask. Okay, so first thing we're going to do is we're going to talk about labeling the parts of a wave. Okay, so number one right here, so the top part of a wave is called a crest. Okay, so that is a crest. The bottom part of a wave, so number two, this is called a trough. Usually when I try to memorize that is it looks like a feeding trough if you've ever been on a farm. And so feeding troughs are always like half of a circle and stuff and you dump into it. Okay, three is going to be your wavelength. Okay, so the important thing here is the wavelength, you start and end in the same place. So it doesn't have to be just a top to top. Okay, it can be a bottom to bottom. Okay, you could do it from here to here, as long as you have one full crest and one full trough. Okay, and then wavelength is characterized by the upside down Y. Okay, that's called lambda. So just if you need that. Number four, that is going to be our amplitude. Okay, so our amplitude is just the distance from the midline to however low we go or however high we go. So amplitude can be right here as well. So that can be our amplitude as well. Okay, and then number five, right here, I call it the origin. You can call it the equilibrium, whatever you want to. It's just your middle line. Okay, so the key thing about the origin is it helps you determine amplitude. It's the center of the wave. Okay, number six, using the formula V equals F times lambda. So I'm just going to write these out real quick so we have everything. Okay, so let me zoom in real quick. So V stands for velocity, and that is in meters per second. Your F stands for frequency, and that is in hertz. And your upside down Y is called your lambda, and that just means wavelength. And that's in meters. Okay, so real quick, I'm going to touch base what frequency and wavelength are again. Okay, so I'm just going to write this up here. So frequency is the number of waves in 1 second. So it's however many waves we can get into 1 second. Wavelength is just the length of one wave. Okay, so frequency is the number of waves in 1 second. Wavelength is just the length of one wave. So, using the formula V equals frequency times wavelength, explain the relationship between wavelength and frequency. So velocity is constant. Okay, so velocity is constant, so that means it does not really change. Okay, the only time it does change is if you were to change medium. So if I went from like air to water, or like a thick rope to a thin rope and stuff, that's the only time velocity is going to change. Okay, if it's just in water the entire time, or in air the entire time, or space the entire time, whatever, okay, velocity is going to remain constant. So if V doesn't change, that means frequency and wavelength are the only things that's changing. And if V doesn't change, that means if frequency goes up, wavelength has to go down. This is called an inverse relationship. And the opposite. If frequency goes down, wavelength goes up. So that should make sense. Remember, frequency is the number of waves in 1 second. If I were to make my wavelength shorter, I could fit more waves in 1 second. So that's why frequency is going to go up and wavelength is going to go down. If I made my wavelength longer, my frequency is going to go down, because if I'm making my waves longer, I can't fit as many waves into 1 second. Okay, so frequency is going to go down. B, explain why the frequency does not affect the velocity. Because if one goes up, the other one goes down. Okay, so if frequency changes, wavelength, I'm just going to abbreviate that by the upside down Y, changes in the opposite direction. Okay, so that's why velocity doesn't change. Because if frequency goes up or goes down, the wavelength is just going to go in the opposite direction. It's like you trying to pour water like into a container that has a hole in it. Okay, so I can keep adding water all I want, but if I have water leaking out just as much, we're not going to go anywhere. Okay, so that's the main difference between frequency and wavelength. Number 7, the two wave pulses below are approaching each other from opposite directions. So I have a wave going to the right, this little one, and I have a wave going to the left on bottom. Okay, so I'm going to zoom in a little bit there. So first I'm going to do is I'm going to find the amplitude of each wave. So the first one goes from 0 to 10, so that means this one is going to be, has an amplitude of 10. Okay, and then my next one is from 0 to negative 20, so this will be a negative 20. Okay, it says, what will be the amplitude of the pulse created when the two waves superimpose? This is just a fancy word for meet. It just means what happens when they reach each other. Okay, what happens when they meet? Okay, if I have a positive 10 and a negative 20 hitting each other, so I'm going to take this 10 and minus 20. So that means when they reach each other, I'm going to get a negative 10 meters for your amplitude. So whenever they hit, so say they hit in the middle, that means my resulting amplitude will look like this. Okay, so when you have a positive and a negative trying to meet, this is called a destructive interference. So this is called destructive interference. So that basically means the waves are on the opposite sides. You have a positive wave and a negative wave, so they're not going to help each other. They're just going to take away from each other. Okay, so that's called destructive. Okay. So coming down here, almost same question. Okay, so I've got two waves coming at each other. So this wave right here, I'm going to go ahead and find my amplitude here. It goes from 0 to 20, so my amplitude is 20. And this one goes from 0 to 25, so this is a 25. So I have a positive 20 wave and a positive 25 wave coming at each other. So what happens when they meet? So when they meet, if they're both positive, they're just going to make each other bigger. So that means my resultant is going to kind of look like this. So what I'm going to do is I'm going to take that 20 plus 25, and I'm going to have a resultant of 45 meters for my amplitude. Okay, so remember the last type of interference we talked about was destructive, when you had a positive and a negative. If they're both on the same side, if you have a positive and a positive or a negative and a negative, this is called constructive. So constructive interference. It's still interference because you're interfering with another wave, but not all interference is bad. Okay, so this is constructive, so you're going to get a bigger wave. Okay, this is like a principle I like to talk about is in wakeboarding, there's a thing called a double up. Stuff is where you do like basically a donut with a boat, and then you pull back through, and so the new waves you're making meet up with the waves that you already made from the donut, and that's called constructive interference because then you get one big wave. Because if you time it right, then it launches you in the air and stuff, so you get more height and stuff. So that's like an example there. Okay, so moving down to the next one. For this standing wave shown, determine the wavelength, the amplitude, the number of nodes, and antinodes. Okay, so we're looking at, so this is called a standing wave. Okay, so first thing we can do is we have our distance for the entire thing. So we need to figure out what's the distance of one wave. We need to find the wavelength. So I need to figure out how many waves I actually have in this distance. So I'm going to follow this. So I've got one wave, two waves, and three waves. So there are 3 total waves in this distance. Okay, so remember, wavelength is you have to start and stop in the exact same place. So I started here and I ended here. So there's one wave right there. Okay, so what I'm going to do, if I want to find the wavelength and I know my total distance is 18 meters, just take 18 divided by 3. That means my wavelength is going to be 6 meters. Okay, my amplitude. Amplitude, remember, is the distance from the origin line, the center point, to the top or bottom. So if I draw like a little line through the middle of this, my amplitude is going to be my distance from the midpoint to the top or bottom. So if my whole thing is 3, my whole top to bottom is 3 on the standing wave, if I want to know the amplitude, just take half that. So my amplitude of the wave would be 1.5 meters. Okay, the number of nodes. Nodes are where you meet in the middle. So this right here, so I'm going to make circles where nodes are. Okay, so nodes are where you meet in the middle. So 1, 2, 3, 4, 5, 6, 7. So this has 7 nodes. Antinodes are going to be where you're at the top. So an antinode would be like up here. So 1, 2, 3, 4, 5, and 6. So an antinode is up here. So I have 6 antinodes. Okay, so moving on to our little bracket here, classifying the types of waves. So we have longitudinal and transverse, and then mechanical and electromagnetic. So I'm going to do like a real quick drawing real quick just for longitudinal and transverse. So transverse wave looks like most waves that you think of. It looks like that nice little wave like that. A transverse wave, I'm sorry, that was a transverse wave. A longitudinal wave is when you, like, if you were to take a slinky and hold it out straight and you just compress and stretch over and over again. So that means you'll have points of compression. So like at first it's going to start off nice and stretched out, and then it starts compressing, and then it starts stretching out again, and then it starts compressing again, and then starts stretching out. So not the best example, not the best drawing, but you kind of get the idea. Okay, so it's just compressions and rarefactions. So if you need to know that, okay, this little dense part right here, I'm just going to draw this up here. It's called a compression. And the stretched out part is called a rarefaction. Okay, so we'll just do longitudinal versus transverse first. Okay, so your sound waves are going to be transverse. Okay, your light waves are going to be transverse. Your ocean waves is going to actually be both. Okay, because one, you have the waves that look like waves that are going up and down, but then they're also longitudinal because the water is compressing and stretching out up and down vertically. So it's actually both. And then the wave in a stadium, this will be transverse as well. So most of your waves are going to be considered transverse. So coming over here to mechanical versus electromagnetic, mechanical needs a medium, meaning you have to have some type of substance to actually for it to occur. Like sound needs particles. Like you need air, you need water. Okay, like a rope would be a medium. Okay, electromagnetic does not need a medium, so no medium. Okay, so these are the ones that can go through anything. So this is why they can go through space and stuff. Like you can go through a vacuum. A vacuum is basically space, there's nothing there. Okay, so like if you were to try to yell or talk or scream in space, you can't do it. Okay, because whenever you hear someone talk or yell and stuff, what you're hearing is sound particles that are being affected, okay, that are being made to move in certain pitches. Okay, in space, there is nothing like that. Okay, so if you try to scream in space, nothing's going to come out. Okay, so mechanical means a medium. Electromagnetic means no medium. So sound needs a medium. Okay, light does not. So that's why you can see the light from the sun, because it can still get here, and there's nothing there between the sun and us. Ocean wave, that's mechanical. You gotta have water to have an ocean wave. The wave in a sports stadium, that's gonna be mechanical. You gotta have people in order to have a wave. Okay, so real quick, I'm gonna talk about the EMR waves so I wanna make sure you know your EMR waves. This will help here in a second. So EMR, this just means electromagnetic radiation. Okay, so these are the waves that do not need a medium. So no medium. Okay, and then they also travel at the exact same speed. So they travel at the speed of light, which is C equals 3.0 times 10 to the 8th. Okay, so these all have they don't need a medium, and they all travel at the speed of light. They all have the exact same speed. So you may see a question like that is, do they have different velocities? No, they all have the same speed. The only thing that differs is your frequency and wavelength. So this you may remember from chemistry. You had the real Martians invade Venus using X-ray guns thing. Okay, so you had radio / TV. Then you had microwaves. Then you had infrared. Then you had visible light. So this is what you can see. So like your colors. So remember your colors that were Roy G. Biv. The red, orange, yellow, green, blue, indigo, violet. Okay, then you had UV. Then you had X-ray. And then you had gamma. So those are your types of EMR waves. So that'll kind of come in handy here in a second when we actually make sure we use the correct velocity. Okay. So number 11, a student timed a pendulum that completed 30 vibrations in 20 seconds. Calculate the frequency and the period of the pendulum. So remember, frequency is just the number of vibrations in a certain amount of time. Period is the time it takes to do one vibration. Okay, so I'm going to have you write down these equations right here up top. So if I want to find period, which is big T, it equals 1 over frequency. But it also equals, this can kind of help you out, time divided by vibrations. Your frequency is the opposite. So frequency is 1 over T. So this would be vibrations divided by time. So that should kind of help you out, because there really is not a ton of math on this test. So, I mean, there is math, but there's very minimal equations. Okay, so I want to count the frequency. I know the vibrations and I know the time. So I'm just going to come up here. I know frequency equals my vibrations over time. So I'm going to do my vibrations, which is 30, divided by my time, which is 20. Okay, so which gives me a frequency of 1.5 hertz. Okay, so that basically means I can fit 1.5 waves in 1 second. Period is just the opposite. Okay, I'm going to take my time, which is my 20, divide it by the number of waves or vibrations. So 20 divided by 30, and I get 0.67 seconds. So that's the time it takes for one vibration. Okay, number 12, how far can sound wave travel? So keyword here is sound. If you don't have this written down already, the velocity for sound is 340 meters per second. So that is your sound velocity. So it wants to know how far can a sound wave travel in 15 seconds. So I know velocity equals displacement over time. So I know my velocity is 340 equals my displacement, I don't know, and my time is 15 seconds.
What was the equation of that one?
Velocity equals displacement over time.
Okay.
So what I'm going to do is I have 340 equals displacement over time. So all I need to do is get rid of that 15. So I'm going to multiply both sides by 15. And I'm going to get a displacement of 5,100 meters. Okay, so the key thing there is just making sure you have the velocity of sound down as 340. And then all you gotta do is just multiply by time to find your distance. Okay, 13. The wavelength of a sound vibrating. Okay, so I'm doing sound with a frequency of 200 hertz. Okay, so my frequency is right here. And I have a wavelength of 1.72 meters. I'm in hertz, I'm in meters, so everything's good. You have to be in hertz and you have to be in meters. So if I want to find the velocity, so remember we have that equation, velocity equals frequency times wavelength. So my velocity is going to equal to 200 times my wavelength of 1.72. Okay, so we're just going to multiply those together. And I get a velocity of 344 meters per second. That's it. So again, we're going to do a little bit of math on this page, but this is the level of difficulty. So it's pretty much just this equation. Okay, so number 14, the wavelength of electromagnetic waves. So keyword there is electromagnetic. From a certain AM radio station is 297 meters. So I have a wavelength of my EMR wave. The frequency of the speakers is 700 hertz. Calculate the frequency of the radio station you're tuned into. Okay, so EMR wave. So I'm going to label this as an EMR wave. So right now, I don't really need this 700 because I'm trying to find the actual frequency of the radio signal itself, not the one coming from the speakers. Okay, so this is the frequency of the speakers. So when I have an EMR wave, that's when you're dealing with the speed of light, C equals frequency times wavelength. So it's pretty much the exact same equation as 13, but now instead of V, we're going to use C. And C is the speed of light. So 3.0 times 10 to the 8th equals frequency I don't know, so I'm going to leave that as F. My wavelength is 297. So I plug that in. It's in meters, so we're good. So now all I do is just take 3.0 times 10 to the 8th and divide it by 297. Just be careful with this as far as your calculator goes. If you do 3.0 times 10 to the 8th, that's fine. If you do the big E trick, that's fine. I always like to put things in parentheses, though, because sometimes your calculator can get confused if you don't put parentheses. So I'm going to take that speed of light and divide it by 297, and you get a frequency of 1.01 times 10 to the 6th hertz. Okay, number 15 deals with the exact same question. Okay, so we're probably going to use that 700 now. So the frequency of the speakers is 700 hertz. Calculate the wavelength of the sound. Okay, so sound being my key word here. So this is a sound problem. So this is where I'm going to do my V equals frequency times wavelength. So remember, the speed of sound is 340. My frequency is 700 hertz. And then wavelength, I don't know, so that's what I'm looking for, so I'm going to leave that as that. So take that 340 and divide it by 700, and you should get a wavelength of 0.49 meters. So 14 and 15 is a good problem to know, okay, because you're basically you have the same problem, but you're using different speeds for different parts. Okay, so watch out for terms like electromagnetic or sound. That usually kind of helps you out there. Okay, number 16, the frequency of waves with electromagnetic. So we're dealing with electromagnetic. From a certain FM radio station are 88.0 times 10, 88.0 megahertz. I was kind of jumping the gun there. So we're looking for a wavelength. So one, this is an EMR wave. So that means we're going to be dealing with speed of light. If you look, your frequency is in megahertz. Okay, so on this review, they actually gave you your conversion tables right here. So that's there. So make sure you use those. So remember, you cannot have something in megahertz. It needs to be in hertz. So mega is just 10 to the 6th. So all you got to do for my frequency is just do 88.0 and then throw on times 10 to the 6th at the end. So now if you just throw on that exponent, you're good. Okay, so I'm trying to calculate wavelength. So, and this is an EMR wave, so that means I'm going to use the C equals frequency times wavelength. So C being my speed of light, so 3.0 times 10 to the 8th, equals frequency, which is now 88.0 times 10 to the 6th. And then I don't know wavelength, so I'm going to leave it as wavelength. So again, here, just watch out for your calculator. If you're going to do this as typed out times 10 to the 8th, please make sure you use your parentheses, otherwise your calculator can get confused. So I'm going to take that 3.0 times 10 to the 8th and divide it by 88.0 times 10 to the 6th. And I get an answer of my wavelength would be 3.4 meters. Okay, everyone good? Do you have questions? Feel free to ask. So 17, green light has a wavelength of 560 nanometers. So one, I'm going to underline this green light. Light is a part of visible light, which is an EMR wave. So that means we're going to be using the C equals frequency times wavelength. But if you look, your wavelength is in nanometers. You can't have that. Okay, so nano is on that chart. It's 10 to the negative 9. So we're going to throw on, so 560 times 10 to the negative 9. So now that's fixed. So I'm going to do C, which is my speed of light, so 3.0 times 10 to the 8th equals my frequency, I don't know, multiplied by my wavelength, which is now 560 times 10 to the negative 9. So take my speed of light and divide it by the wavelength. Okay, and you're going to get a frequency of 5.4 times 10 to the 14th hertz. Okay, 18. A series of waves moves along a wire with a speed of 90 meters per second. So already I have a velocity. And I have a wavelength of 7.6 centimeters. I can't be in centimeters. Okay, so if you ever want to go from centimeters to meters, just divide by 100. So 7.6 divided by 100 gives me 0.076 meters. So it wants to know I need to find the period and the frequency. Okay, so just because it says period first doesn't mean you have to find period first. You can. Okay, so, but I'm just going to keep doing what I'm doing as far as my equations. I'm going to do V equals frequency times wavelength. So my velocity is 90. My frequency, I don't know. That's what I'm looking for. And my wavelength is now 0.076. So take 90 divided by 0.076, you get a frequency of 1184 hertz. So there's one part of my question. So I went and I found frequency, so I'm done with that. But remember, if you want to find period now, if I know frequency, remember period is T equals 1 over F. So 1 divided by 1184. And that gives me a period of 0.0008 seconds. So that's how long it takes for one of those waves to complete a wave. Okay, getting there, almost done. A bat emits an ultrasonic sound frequency with 55 kilohertz to aid the location of obstacles. The speed of the emitted waves is 335 meters per second, so I know my velocity. I know my frequency, but your frequency is in kilohertz. So kilo is on that chart. So kilo is 10 to the 3. So I'm going to do 55 times 10 to the 3. So that's kilo. So I know my velocity, so I'm going to use my velocity equals frequency times wavelength. Velocity is 335. Frequency is now 55 times 10 to the 3. And my wavelength, I don't know, so I'm going to leave it as that. So take 335, divide it by 55 times 10 to the 3. And you should get a wavelength of 0.006 meters. Okay, I think that's the gist for the math equation, so we're pretty much done with that. So not a whole lot of math there. So I mean, we did a lot of math, but pretty much the exact same equation, just different speeds. Okay, so last part. 20, define and diagram the following for a 2D wave. So we have reflection, refraction, diffraction, and interference. Okay, so reflection is exactly how it sounds. I'm going to kind of zoom in for this. So say I have a surface like this. And let's see, I have a light wave coming in like this. Okay, so that means my light wave is going to reflect off like this. Now the key part here is this middle line right here. So your reflection angle, so your incidence angle, which is the one you came in with, is going to be the exact same angle as your reflection angle. So I'm going to write that over here. So incident angle is equal to your reflection angle. Okay, so not a whole lot new there. A lot of people know what reflection is. Okay, so refraction. So this is when I have a surface. Okay, I have a light coming in. But then when it hits that surface and goes through it, so like going from air to water, okay, it's going to bend it. So this is basically the bending of light waves. When the medium changes. Okay, so like this is why if you're, I think they use this example in class, if you stick a pencil in water, it looks like it's bent. Okay, or like if you're ever sitting on the edge of a pool with your legs in the water, it always looks like your legs are just snapped and stuff like that. They're bent. That's called refraction. Okay, so diffraction. Okay, so this is when I have a surface, like where I have an opening. So I'm going to draw a thick wall here. Okay, so this is when I have waves that are coming in, like this. And then they bunch up right here whenever they hit this opening, like a door. And then whenever they get through that door, it's like all of a sudden they're free. And they just start expanding. Okay, so it's no longer just nice, even lines. It's like they clustered up in the beginning, and then as soon as they break free, it's like they're free. They just start going off in different directions. Okay, so that's basically the gist of diffraction. Is like you have light waves going through an opening, and then whenever they go through that opening, they spread out. Okay, interference. Okay, so we talked about a little bit about interference earlier. We did constructive and destructive. This is like kind of like what it actually looks like. So say I were to throw something in the water right here, and it made waves. And let's say I threw something else in the water right here, and it made its own waves. Okay, so whenever these meet up, so like right here, right here, right here, right here, right here. Okay, they're either going to help each other or it's either going to be constructive or destructive. It just depends on what the wave is at that point. Okay, so the point is when you have a wave and another wave meeting with each other, that's called interference. Okay, so one wave is interfering with the wave of another. Okay, last little bit I want to talk about is because it wasn't really on this review is whenever you had like a wave going through. So let me change my colors real quick. I'm going to change my size. So when I had like a thick rope, like this, and then it went to a thin rope, okay, so if I send a wave down with a thick medium, like a bigger medium, and it hits this smaller medium, your velocity is going to go up. Okay, so as it gets to this easier rope, a lighter rope, that velocity is going to take off. Okay, because it takes a lot of energy to move this big medium, and then that same energy is transferring over to an easier medium, so it's going to go faster. And whenever you hit this wave right here, like whenever you change mediums, if you're going from a thicker to a thinner rope, part of it's going to reflect back in the same direction. So just part of that wave is going to come back in the same direction. Now if I were to go to, let me switch my size again, a thin rope to a thick rope, okay, so let me switch over real quick. When I go from a thin rope to a thick rope, my velocity is going to go down. Okay, so I'm going from an easy medium to a little bit more difficult medium, so my velocity is going to slow down. Also, whenever you go from a thin rope to a thick rope, part of that's going to reflect back, but it's going to reflect back in the opposite direction. Okay, so whenever you go from thin to thick, velocity slows down, and then part of that wave is going to reflect back in the opposite direction. So meaning I had a crest in the beginning, it's going to come back as a trough. Okay, so that pretty much covers the gist of waves. So hopefully that kind of helped out.